Okay, so I'll code the solution to the second problem. So here we defined our functor, which should have been defined for the previous problem. And so I think it was called eval, and it produced a either an int or a division by 0, which contained our div, I believe, and with an int. And so eval takes an expression, produces either a division by 0 or an int. We're going to have to import scala z. And so we do kata. Oh, we need to use kata m because there's the possibility of failure. And so in order to eval, if we hit num lit, the solution is relatively straightforward. So it's just, so if an expression is just simply a literal, it's going to just be the value. And we need to do dot write because there's no failure in that case. And then if we hit an add expression, where the left and the right, as previously, are some previously computed result, then we simply need to add the left and the right together. And once again, in this case, there's no possibility of failure. So we simply lift it into the right disjunction. And then finally, the most interesting case, if we have a division, then if our denum is equal to 0, then that means that we have a division by 0. And that's our failure case. And otherwise, we have we just divide num by denum. And that's going to be the success case. So that should be our implementation. Although, yeah, how about I just try this? I'll copy this, create some new thing, paste it. Okay, never mind. Thank you guys for letting Scasti get back up. So oh, I guess it missed. Oh, let me just repaste this. Why is, oh, I guess I missed. Okay, let's see if this works. Not found matriosh. Oh. Yeah. Okay, so this is basically looks correct-ish, except that we don't have an expression. Yeah, and then the other problem too is it's because of Scala inference sometimes is kind of not great. So what we can do here is since we don't have kind projector, we'll say that we have our monad that's essentially division OR, and we're going to say that that's a division by 0 or an A. And then here in kata M, we can say that our monad is this division OR, and then we're producing an int, and then hopefully this will work. Not. Oh, okay. And then the interesting thing is, if we want to use kata M, we now need to define an instance of traverse for our expression. So basically, like if you're using Matryoshka, you end up mostly just implementing traverse for all your data types, which is once again relatively straightforward. So traverse, I believe we need to implement traverse implementation, which I don't know if anyone's familiar with the signature of traverse implementation. I think it takes some kind of G and then an A and a B, and given an expression of A and a function from A to G of B, will produce a G of expression of B. I believe that's correct. And then what we need to do, in the case of numlet, we just need to lift into G. In the case of add, what we'll do is apply our function and use the applicative. And kind of same idea for div. Okay, so now we should have an instance of traverse, and kata M should work for us. Scala is complaining about needing an import for higher kind of types. Oh, right, and our G needs to be an applicative. So what's this error here? Polymorphic expression cannot be instantiated to expected type. Oh, right. So this, it's just kind of we just need to tell it that numlet is actually an expression of B. And I think it'll be happy. Okay, hooray. Our eval function produced 7. And let's say we were to replace this division with a division by 0, and then execute it, we would get division by 0. And so notice how simple, I mean, yes, there's a little bit of initial setup over here, but this is like you do it once for your data type, and then after that, all your recursive algorithms are very, very simple. Hopefully you're convinced. Okay, next exercise. So I don't know what old, yeah, yeah. Hopefully you guys have. So who has this, like, roughly this code up on their computer? Okay, that's what I thought. So maybe I'll just make this I'll just code it and explain what I'm doing, since this whole scarcity thing went to. Okay, so exercise number 4, collect nodes of a certain type. So we want to implement a collect function. So we'll get rid of this eval. Write a collect function that takes a fix of expression and is going to return a list. What just happened there? Collect, it's going to return a list of. So this happens sometimes. You want to just collect some, one of the leaf nodes in your expression. So if we want to do that, we can use kata, and the result is going to be a number literal. And so in the case that we hit some number literal, we'll just return the number literal. And in any other case, does someone know what the implementation is for any other case? We're trying to collect all the the literal numbers in our expression.
Collect them into what? Flattening to a list?
Yeah, like yeah. So collect takes an expression and produces a list of all the number literals in the expression.
Is it just something like cons? That seems to be.
Cons, what do you mean cons? So cons takes an element, so what would the element be? So you guys are saying, oh, so you guys are saying that I should say add here? Add left and right. And then what am I doing? Left concatenate with right. Okay, and then we can do div of num and denum, and then just do num plus denum. So that's one option. We can do that. The problem with this is that let's assume that our expression language had many more nodes, and really all we want to accumulate is num literal. We'd have to write all these, add, div, let, all these things. Since we have an instance of traverse for our expression, we can actually just say, in all other cases, we want to just fold it together.
Why in the numlet case don't you return?
No, you're right. That's a very good observation.
Could you make that bigger by chance?
Is this better?
Yeah.
Okay. So it just so happens that list has an instance of monoid, and our expression has an instance for traverse. So if we called fold, it'll basically just join all the lists together. So this is kind of a neat way that all the other expressions are just handled by folding them together. And so then presumably, yes? Oh, sorry. Thought you were asking a question. If we call collect, we will get, I think there were 2. Numlet takes, oh yeah. So what's this error? Type mismatched, required list of numlet found.
Now list is not a type, right? Or it is?
Actually, it is in Scala, and which is kind of convenient here. What is this error? Type mismatch. Oh, right. Okay, this is. This is producing a list. There we go. So we've collected all the different num literals in our expression over here. Okay, that was that exercise. So exercise number 5 is an unfold. So this one's kind of interesting. So Matryoshka and recursion schemes in general defines folds. So folds, you take a recursive data structure like an expression language and you produce some result. You know, in the case of eval, we're producing some int. So an unfold is the opposite. You start with some value and you're building up a recursive structure. And so the kind of poster child for unfold is an anamorphism. So in this case, what I'm asking you guys to define, although I'm not really asking anymore, is oh yeah, what was it called? Gen. So what we're going to do is we're going to implement a function gen, which takes an integer. Basically, we're doing the opposite of that initial example I showed you guys, which is to calculate the complexity of an expression. So in this case, we're going to accept a complexity, and we're going to generate some arbitrary expression of that complexity. So what we need to do that is we need our fixed data type. So we're going to say fix of expression dot ana, and what do we stick in here? So here it's the opposite way around. This one I actually didn't do in advance, so it'll be interesting. So we can say, so what's the, it helps to start with the leaf case. So what's the leaf case? If our complexity is, we'll ignore complexity 0 because I don't know what that would be. So we'll just, I could do like a guard, or we could even return option. Well, actually, let's do that. Let's be proper here. So let's say that our complexity returns an option, because if you pass in 0, then there's no expression that you can generate with complexity 0. So the fact that I'm using option, what does that mean? I can't use ana anymore. What am I using instead?
Ana M?
Yes. One person's following. So we're going to use ana m. And so now the case where we get a 0, we can simply return none.
If it's less than 0, I'm integer.
Okay, so if it's something that is smaller than 1, we'll return none. Good catch. If it's 1, then we will simply generate a numlet. So we'll say fix of numlet of, whatever, doesn't matter. And then in any other case, what we'll do is, I don't know, I'll make it as simple as possible. We could do something like let's have fun. Let's say if this number is, I believe this is like this. If x is an odd number, so that would be x modulo 2 not equal to 0, then we'll generate an add. And so this is an interesting one. So add takes 2 parameters, but what do we supply as the left and the right side? So ana m works much like kata, except in the inverse direction. What's the type of the thing that we're putting here? int, exactly.
Yeah, things that the complexity go up.
Yep, exactly. So this is like the magic kind of recursion scheme thing, is you don't have to call recursively things, so you're basically just giving back that initial complexity, well, not the initial, but like, you know, you're letting it unfold for you. So you're saying, okay, I've unfolded one step, and like I'm creating an add with the new value of complexity, and like you do the recursion for me. And if we say, in all other cases, we produce a div, once again, decrement the complexity by 1 and let the recursion be dealt for us. So now presumably if we call gen, say what? Yes, thank you. Good point.
You have to wrap them in fix as well, or no?
Yes, I do need to wrap them in fix as well, thank you. Although, yeah. So now presumably if we gen 3, I believe it'll generate some arbitrary expression of so what's the error? Expected class or object definition. That's not good. What's missing here? Oh, I believe this guy was extra. So fix or expression. Interesting. How about if I give our monad and our result type? Is that gonna? Okay, so we'll have some, let's go look at so as the keynote last night was mentioning, let's go and read some code. So in Matryoshka, we've got our data, that's where most of the interesting things happen. And what we're interested in is co-recursive. And co-recursive has Anna here, and I'm not sure what, so, and we have implicits. Anna M takes, So what is missing here? I believe that maybe, that might work. Maybe not. Maybe I should have done it before. Not enough. Oh, because fix is the constructor, it's expecting a functor. What am I missing?
Did you take your functor definition out of your object, or is it
No, I believe it's still in there. There's an instance of traverse. No, this should, okay, there's definitely no parentheses there, but fix should have an object. if we look at fix, fix has an object and an instance. So, I mean, we could always just try co-recursive directly, I suppose. Okay, well, I won't debug this here, but there's something I'm missing, but it's cosmetic. This unfold is semantically sound, pretty sure. Okay, next. Okay, so here I have a kind of like a quiz. So, you know, a naysayer might say, okay, cool, this stuff is kind of cool, but like, what if I just define a trait tree and say there's some abstract list of children, and then define some transform function? This you could actually implement with children, and then just have everything that derives, then just have any of your recursive data types extend tree and basically say what their children are. So what would be the difference over this and, you know, kind of recursion schemes that I've just shown you? Anyone? So this is kind of a question I ask myself. I, you know, try and be fairly skeptical of anything. So this would actually work in the case where you're just transforming a tree to a tree. So if you have an expression or some kind of recursive data structure, and all you're interested in doing is transforming that data structure, but into the same data structure, then you could do this. But anytime you want to do some kind of fold or unfold or more complicated thing, and I haven't gone over some of the more complicated recursion schemes, then you need your data type to be a functor, so that, you know, basically the library can stick an A in there. Okay, so this one's kind of interesting. Well, we're going to go back to, oh no, never mind. This one I'll skip. So this is interesting. So actually what I'm going to do here, I'm going to get rid of this and go back to eval, which I believe was, or actually we'll go back to increment. So does this work? Okay, that works. I'm going to get rid of Matryoshka. So actually, let's just re-implement the parts of Matryoshka that we need in order to make this work. It's actually not that complicated. So here we've got our fixed type over here. So I'm going to just define fix. So what's the type here? So this is our fix class that we've been using to make our expressions recursive again. And I'm giving you a hint. Fix only has one parameter. I just want you guys to tell me what the type of it is. Say what?
Yep.
F, okay.
Bracket fix.
Yeah.
And
And F? Yeah, nice, exactly. And so it's kind of interesting. It's a little bit mind-boggling. It's like two functor things kind of cancel themselves out. So yeah, that's the definition of unfixed. This allows us to fix our infinite functor. And so now if we wanted to implement kata, how would we go about doing that? Say what? No, we don't need to pattern match. So I'll give you a hint. There's actually something missing from our type signature. I think I hear the answer there. We do need what? We need a functor, exactly. So in order to implement this, we need to have proof that f is a functor. Okay, now we have proof that f is a functor. Now what do we do? Map? That's probably yeah, that's what's great about parametricity. So there's not a whole lot of ways you can get this implementation wrong. You just need to think of what it is. So we've got our f, we're mapping. So now we've got we've got our a. So what do we do with this?
What else A is?
Well, because it's an f of a. Oh no, wait a minute. What am I doing here? So unfix. So we're mapping over unfix, which is an f. And inside is a fix. So what do we do? Yep, we recursively call kata. So this is where we're allowed to do recursion because we only implement the recursion once. So we call kata with our f. So this actually, so you know what? I was wrong. This, say what? Okay. This actually, I believe, will compile, but is incorrect. What is missing?
We still are returning.
Unfix in recursion?
We still haven't gotten to A.
Exactly. So we've called recursively f on all of our children, but we are ourselves an f, so some kind of expression we need to call f on ourselves. And then now if we run, this should work. So really, all we've been using in Matryoshka so far are just these 4 lines of code.
So this doesn't stack over.
I mean, if your expression is like enormous, it might, but I don't. Yeah, I mean, it's the same. It's the same thing as if you implemented like the recursion yourself. Well, actually, does it stack overflow? Yeah. It like I don't think it can do tail optimization with this. So that. But when you think of it, like in the general case of recursion, if you were doing it ad hoc yourself, like in some cases it wouldn't be able to do this. So in this case, it's just, I could never do it. So there might be some cases where if you hand rolled it yourself, you could like make sure that it was tail recursive. But in this case, I believe that you just have to accept that that like your structure. But I mean,
Your F is not.
then maybe. But I would say that in a lot of cases, your F is actually not that big. Like I think that Matryoshka, I mean, like a common use case is for this like kind of languages, and typically like an expression in a language I don't think would be big enough to yeah. Okay, so we implemented fix. That was kind of easy. So this is kind of an interesting one. So if we go back, so let's move beyond kata. So far we've been using kata. Okay. Let's use one that requires another kata, or another recursion scheme. So what was our first? Right, this one. So if we go back to our eval example, and let's get rid of fix because I don't want to implement the one that we need, which means we need to add back Matryoshka.data.fix and Matryoshka.implicits, and changing this. So does this still work? Okay, we got our division. So the problem here is, what if, so here we're saying our division by 0 error class takes a div of int. So it takes, what does that mean? It takes, it takes a div, which is, a numerator and a denominator, but where a are ints. So essentially what that means is, let's say you had a really complex expression where div is some complex expressions. In your error message, you would only get let's say that the top expression resolved to like 4, and then the bottom presumably resolved to 0, then it would say, okay, you tried to divide 4 by 0. But maybe that's not super useful because you actually want to see your original expression to understand exactly why 0 ended up in the denumerator. So we could change our error class to say, okay, no, it's going to return, instead of a fix of int, it's going to return a div. Instead of a div of int, it's going to return a div of fix of expression. So it's going to return, we know it's a division. I mean, we could even just put fix expression here, and that would be fine. I mean, it would just be like, oh, this expression yields a division by 0, but we can be a little bit more precise because we know that a division by 0 is only going to ever be a div. But we're going to say that the things being divided are expressions as opposed to resolved numbers, so that we can actually understand exactly what happened. But now that we change the type signature, we're going to get a problem here, right? Because we're trying to construct, we're using this D here, D being this division, and this division, because of the way recursion schemes works, num and denum are the pre-evaluated results of the sub-expressions, and so this is a div of int, and yet our error requires a div of fix of expressions. So what we can do here instead of using kata, we're going to use one called para. And what para does is it not only gives you the computed result, it also gives you the original expression. So para is going to give us, everywhere where there's an A, we're going to get both the previously computed result and the original. So in the case of add, we'll get a tuple where I believe the left-hand side is the original result, and the right-hand side is the computed one. So in the case of add, there's no possibility of failure, so we don't really care what it was before. We just care what the computed value is. However, in the case of div, we do care what the original value is. So I'm just going to call this onum for original num, just for conciseness, and odenum for original denum for conciseness. Okay, and now if our denum is equal to 0, our computed value of the denominator is equal to 0, are not equal to 0, then that's fine. But if it is equal to 0, I'm going to make this slightly smaller for now, then we can return the original result, which is going to be a div of the original numerator and the original denominator. Does this compile? So here, it tells us, okay, there's a division by 0 here, but it actually gives us the original expression as opposed to just the computed values. Any questions? Okay, so that's para is pretty simple. It's essentially the same thing as Anna, but allows you to see both the old and the new. So I don't have time to finish this one, but I'm going to note that Scala-Z defines a co-free structure, which I'm sure is useful for a bunch of stuff. I'm actually not aware of all the things it's useful for. But one kind of neat thing about it is that it works really well with our fixed point data types and recursion schemes to annotate expression trees. So if we look at actually, I can just get to it from Matryoshka if I go into recursive and look at Cofree. So Cofree has an S and an A. And so our S here can be our functor, and the A is the annotated thing that we want to add to our functor. And so if we had a cofree of expression, then at every node we could annotate some A. Like let's say this would typically be useful if you have some you're writing a compiler, you have some expression and it's a type language, so you would annotate the types using cofree without actually modifying your original data structure, which is kind of really neat. And then you could use cofree to get your annotation, or get, and this is the kind of neat part, is when you call tail, so this is kind of small, but when you call tail in cofree, you get a cofree of S of A, which means that the A in our functor is going to be a cofree itself, which means that every single node in the, and it's kind of, it's one of those like recursive, like type hole things again, kind of like fix. So that's kind of a neat thing. That's all I'll say on that. And then the last thing I wanted to show. So actually, this one is open to you guys to solve because I don't have the ideal solution for it. So what the problem here is, let's say we extend our expression language and add a let clause. And so we're going to say a let is some ID. So we'll add an ID to our language as well. They kind of go together. So you can encounter in our new language, you can encounter an identifier, which is simply a string. And that's an expression. Or you can encounter an ID, or a let expression, which would have an ID, and then an as, which is what the ID is supposed to represent, and an in what expression it represents that. So now that we've extended our language, we need to implement traverse. So that's pretty straightforward. In the case of an ID, so what do we do in the case of an ID? Yeah, exactly. So we're doing the same thing as numlit. It's a leaf node, so it's really relatively straightforward, except for having to coach Scala into understanding that this is an expression. So we point it into G, and then in the case of a let, what do we do in the case of a let? So we do same thing as the other ones, apply our function to our two recursive values, and just build back up our let. Okay, so we've extended traverse. So now if we wanted to implement eval, how would we go about doing that? Well, we need to add cases for our new nodes. So we've got our ID has some value. So what's the implementation of ID? Let's go back to kata and stick this back to int. Then we can simplify this. So before So the reason why this one is kind of an open problem is because I actually don't know what. So I have one idea for a solution, but I don't think it's a very good one at all. I'm sure there's a better one. The problem with this one over here is that like when we see ID, we don't know, like ID represents some other expression, but we don't have any notion of scope here. And certainly with kata, this is impossible because let's remember that any leaf node, despite the fact that it's got an A, doesn't actually have an A in here, which means that ID is only ever going to convey the information that is the string that it is. Like there's no way, there's no recursion scheme that we can use where this is going to change from a string. So there's basically no way using kata or most of the recursion schemes where we're going to have the information that we need at the case of ID in order to substitute ID and well, to substitute the expression that ID represents with its like computed value, and return that. So, really, so the solution that I can come up with, I believe would work, but is not ideal, is we can say if we encounter a let expression that has some ID and an as and an in, then we can take the in. The in is a we fix the in because it's a no, never mind, this doesn't work. Oh, no, right, okay. So we would have to use para. If we used para, then, yeah, I'd have to change all these again, but basically our in, we would get the old value and the new value. Right, and then with the old value, we could fix it, and then we could kata over that, and basically, I won't write all this out, but like whenever we encounter a AID node that has the value, so whenever we encounter ID, we would, so this notation is like a stable identifier in Scala. It allows you to, instead of assigning to ID, you're just comparing on ID. So whenever we would encounter ID, we would replace that with as, and in any other case, we would not do anything. But then, so now we would have a new expression in where we've replaced all instances of ID with as. So then what would we do with that? So this is where lies the problem. We would have to actually call recursively eval unreplaced. Yet I read to you earlier that ad hoc recursion is like evil and whatnot. So this is not, this is not ideal. But I believe this would work. And then in the case of ID, I mean, whatever, like we could implement anything, because the idea is that we would actually never hit that case, because we would always, or actually, no, that's not true. Here we would have some kind of, like, I'll just do division by 0, but it would actually be any ID that we would encounter would be one that didn't actually have a binding. So it would be like an unknown identifier. But yeah, so this should work. But the problem is that we're still using recursion. We're using less recursion than if we weren't using, recursion schemes in some fashion. But I would be curious to see if there is a fold that we could use in this case that would allow us to get rid of recursion entirely. So if someone knows what the answer to this problem is, I would be really interested in hearing the solution, because it seems to me like a pretty straightforward problem. I mean, we've only extended our expression with this pretty straightforward and common nodes, and yet now writing an eval function has become a whole lot more complicated. So I
just remove the ID node instead of just have like a string let node.
say that again.
So just remove the ID node from the type.
Oh, okay.
Like have the string actual let instead of
right. And okay. And then so the in.
So let a ID equals string. I mean,
Right. Yeah. Okay. Whatever. Yeah. But the problem is, like, in here is an expression, so like it could never be an identifier. It's like, how does that work?
Normally you would have some evaluation context, I think.
Well, yeah, definitely. I mean, and that's essentially, yeah. I mean, like if we were just implementing this with like traditional recursion, presumably we would have some inner recursive function that had some scope state, and so then you would just call that and like update your scope. But then you'd have a whole bunch of recursion, which is what we're trying to avoid, right? We're trying to avoid doing recursion ourselves. So yeah, I don't know. Like open problem. I'm sure there's a solution, but well, I'm not sure, but I'd be curious to hear if there is one. So yeah, so that's most of what I've got. Hopefully, it's kind of gave you an idea what Matryoshka and recursions are.
So how does the performance of the cut and cut-m, how does it work underneath? Is it create a while loop for you?
So they when we implemented fix, that's essentially how it's implemented in Matryoshka. So there's no while loop. But that being said, I mean, if you really wanted to, you could never mind turtles all the way down and implement kata and fix with a while loop if you really wanted to. There's nothing stopping you from doing that. But in Matryoshka, that's not the case.
So it's just recursive calls?
Yeah.
Overload the stack?
Yeah, exactly. Yeah.
What type of one you use kata m? How do the recursions go in kata m?
So let's say you were to use like a ad hoc recursion and you had some monad. What you would end up doing is like mapping over the monad constantly. So like your function would return m of a, and whenever you call recursively m of a, or your recursive function, you would get m of a, so you just like map over that. So like Matryoshka, yeah, our flat map. Yeah, exactly. So Matryoshka is just doing that for you. So like it's kind of really nice because then, when you do your cases, it's just, you can kind of assume the happy case. You can be like, oh yeah, I got like my nodes contain the computed result already, even though there's a possibility of an error. Like Matryoshka will handle that. If there's an error lower down, it'll just like bubble it up. But when you're expressing your algebra, you can just assume that everything went well. So yeah, it's just basically calling flat map for you. But I mean, it's one of those things that it seems simple, but once like it's just, it's like savings over time, right? Every single one of your recursive algorithms is like that much simpler. It makes your whole code base a lot simpler. Any other questions? Okay.
Technically, you can make a kata m stack safe, right? If your m is not rec, for example.
I think so. And like the gentleman was suggesting earlier, like you could always just implement kata with a while loop. Well, I think so. I mean, I haven't, but I think you could. And if you did, well, I don't know, it would increase the chances of your library having like a bug in it because, I mean, it's a while loop. But it would probably make it more stack safe, I think.
You could make it stack safe because co-free installs out as trampoline, so it's stack safe for unfolding.
You kind of M or NM through trampoline and you run, but still not that efficient as trampoline.
Cool. Well, thank you.